SwayamPrabha. Digital India. Educated India.
Now we would like to consider determination of planes of maximum shear stresses at a point. Let us consider that the stresses at a point are given by the tensor sigma ij, and from this you can determine the principal stresses sigma 1, sigma 2, sigma 3 and their directions. Now, we would like to consider reference as the three principal directions. So, these are the principal directions. Now, it is coinciding with sigma 1 and this y, let us say it is coinciding with sigma 2 and this z coinciding with sigma 3. We consider one plane with reference to these directions whose outer normal from the origin, let us say it is oriented like this, its direction cosine, let us say L, M and N. We would like to now find out a plane ABC such that this plane will have the maximum shear stress. So, the shear stress which is going to act on this plane, let us say which is parallel to this plane, is equal to tau, and the stress which is going to be acting normal onto this plane is sigma. So, these are the two stresses, and we would like to see what would be the orientation of the plane ABC such that this shear stress tau is going to be maximum. Now, on this plane we can find out the tractions in the three reference direction. So, we will have tractions in this direction S1, so this is S1, and similarly in the direction we will have S2, and in the direction of Z which is going to be this direction. So, therefore, this is the direction which is going to be, let us say, S3. So, we can write now S1 to be equal to, using the Cauchy formula, L into sigma 1 m into 0 plus n into 0, because tau yx and tau zx are 0. So, therefore, these tractions on these planes are going to be simply S1 is L sigma 1, and by the similar type of considerations, you will find that this traction is nothing but m sigma 2, and the third component is nothing but n sigma 3. Now, if we try to consider the normal stress, since these are the tractions on this plane, the forces acting on this plane would be nothing but the area of this plane multiplied by the traction. So, there will be 3 traction acting in the 3 orthogonal directions, and if we calculate the resultant or if we take the component of those traction in the normal direction, that should give us the sigma stress. So, we can now write that sigma stress is now equal to component of this is acting in one direction. So, therefore, angle cosine of the angle is L. So, therefore, L into S1 plus m into S2 plus n into S3. So, therefore, this gives us L square sigma 1 plus m square sigma 2 plus n square sigma 3. So, this is nothing but the normal stress. Now, if we calculate the resultant of the 3 tractions, so total traction is can be obtained by vectorially adding the 3 tractions. So, therefore, it should be equal to S1 square plus S2 square. So, in fact, we can write S square equal to S1 square plus S2 square plus S3 square, and therefore, we have S square is nothing but L square sigma 1 square plus m square sigma 2 square plus n square sigma 3 square. Now, if the stresses acting on these planes are on this planes are sigma and tau, these are the 2 stresses only acting on this plane, we can also find out the traction from the consideration that it is nothing but vector sum of the 2 stresses sigma square plus tau square. Note that this is possible to add vectorially because of the fact that we are considering the same plane, and on this plane the tractions are acting in the 3 directions of magnitude S1, S2 and S3, and at the same time we have alternatively the stresses sigma and tau. So, we can now get the value of the shear stress, which is going to be given by L square sigma 1 square plus m square sigma 2 square plus n square sigma 3 square minus we have the value of sigma, which is L square sigma 1 plus m square sigma 2 plus n square sigma 3 and it is whole square. Now, we also have the relationship that sum of the 3 direction cosines, square of the sum of the 3 direction cosines, L square m square plus n square equal to 1. So, if we know if we now eliminate n square from this, we have, so if we would like to consider that this is relation number 1 and this is relation number 2. So, using 1 and 2 we get, we would like to have this L square sigma 1 square m square sigma 2 square plus 1 minus L square minus m square into sigma 3 square minus L square sigma 1 plus m square sigma 2 plus 1 minus L square minus m square into sigma 3 whole square. So, this is nothing but this is tau's square. Now, if we have to get the maximum value of tau, we can differentiate this relation and see that delta tau delta L and delta tau delta m is equal to 0. So, if tau is maximum, so for maximum tau we must have, it has 2 variables related to it, L and m. We can think of considering delta tau delta L 0 and delta tau delta m equal to 0. So, if we take the first, let us say that this relationship is 3. So, from 3 we will have differentiation of both sides will give us 2 tau delta L is equal to 2 L sigma 1 square minus 2 L sigma 3 square minus 2 times L square sigma 1 m square sigma 2 plus 1 minus L square minus m square sigma 3 multiplied by differentiation of this quantity will give us 2 times L sigma 1 minus 2 times L sigma 3. So, therefore, we will have 2 times L sigma 1 minus sigma 3. So, now, if we take this is again sigma 1 square minus sigma 3 square into 2 L. So, there is sigma 1 minus sigma 3 is common factor, and if we make use of the condition delta tau delta L equal to 0, this will give us, we will have 2 L sigma 1 plus sigma 3, taking sigma 1 minus sigma 3 out, minus 4 times L, this is now L square sigma 1 minus sigma 3 plus m square sigma 2 minus sigma 3 equal to 0. So, we can this is going to be m square sigma 2 minus sigma 3 plus we will also have a term, I am sorry, we will have a term here which will be left is nothing but it is sigma 3. So, the terms within the bracket will be L square sigma 1 minus sigma 3 m square sigma 2 minus sigma 3 plus sigma 3 will be there. Now, if we try to take L common and then we rearrange, this equation will become like this, L into sigma 1 minus sigma 3 m square sigma 2 minus sigma 3 minus sigma 1 minus sigma 3 by 2 equal to 0. So, this is the equation which we obtain by using delta tau delta L equal to 0. So, let us say that this is equation number 4. Similarly, if we try to differentiate this relationship, if we differentiate this relationship with respect to m from both sides, we are going to get. So, again from 3 we are going to get twice tau delta m delta L is equal to 2 times m sigma 2 minus sigma 3 into L square sigma 1 minus sigma 3 plus m square sigma 2 minus sigma 3 minus sigma 2 minus sigma 3 by 2. So, this is the expression. Again, if you make use of delta m delta L equal to 0, this will give the relation m into L square sigma 1 minus sigma 3 plus m square sigma 2 minus sigma 3 minus sigma 2 minus sigma 3 by 2 equal to 0. So, this relationship, if you indicate by 4, I am sorry, let us indicate it by 5. So, this equation 4 and equation 5, you have two equations to solve for L and M, and you can make use of the relationship that L square plus M square plus N square equal to 1 to get N. By solving these two equations, you can see that immediately the solutions are L equal to 0, M equal to 0. So, if we consider the first root to be L equal to 0 and M equal to 0, then N is going to be equal to plus minus 1. Similarly, if you consider L to be 0, then M comes out to be plus minus root half. So, if you just consider L equal to 0, then from equation 5 you get M equal to plus minus 1 by root 2. So, if you put L equal to 0 here, then from this equation M square into sigma 2 minus sigma 3 minus sigma 2 minus sigma 3 equal to 0. Therefore, this will cancel and it will give you this. And again, making use of the fact that L square plus M square plus N square equal to 1, you get N equal to plus minus 1 by root 2. Similarly, if you consider in this equation M equal to 0, so if we consider M equal to 0 and if we substitute M equal to 0 there, then in this relationship we are going to get L square into sigma 1 minus sigma 3 minus sigma 1 minus sigma 3 by 2 equal to 0, which will give rise to plus minus 1 by root 2, and again N is equal to plus minus 1 by root 2. So, these are the three sets of solutions. One could get the set of equations written in terms of L and N rather than L and M, and if we have equations going through the procedure in terms of L and N, we will get another 3 sets of solutions, and again if we make use of combinations like N and M, we are going to get another 3 sets of solutions. Finally, you will find that the solutions you have really some repetitions, and the distinct planes that you are going to get, we would like to give you them. So, finally, the solutions are so if we write now L, M and N, then you can have 1, 2, 3, 4, 5, 6. Although you have 9 solutions, you will find that there are 4 distinct combinations, and these would be plus minus 1, 0, 0. This is 0, plus minus 1, 0, 0, 0, plus minus 1, and then we have 0, plus minus 1 by root 2, plus minus 1 by root 2, and plus minus 1 by root 2, 0, plus minus 1 by root 2, and the last one is plus minus 1 by root 2 plus minus 1 by root 2, 0. These are the 6 planes. If you would like to find out the solutions, you find that this particular case, it corresponds to, let us try to consider our reference. So, if we take our reference as the principal directions sigma 1, sigma 2 and sigma 3, this is the direction which is making an angle of 90 degree with the sigma 1 directions. Therefore, what you find is that this gives you the plane of the principal shear stress, and in this case it really indicates that there is no shear stress. Similarly, plane 2 would indicate this plane, if you would like to call it this origin to be represented by O. So, this OBC. So, therefore, this is the plane. The first one represent the plane OCA, second one is nothing but OBC, and the third one, it is nothing but OAB. I am sorry, it should be that this plane is OCA and this plane which is making an angle of 0 with sigma 2. So, it should be OAB, I am sorry, or OBA. So, this is the plane OBA and this is the plane which is making an angle of 0 degree with the direction 3. So, therefore, this is nothing but the plane OBC. Now, the plane number 4, this is making an angle of 45 degree with the direction, it is making an angle of 45 degree with the principal directions 1 and 2. So, it is making an angle of 45 degree with the direction m and n. So, therefore, it means it is making an angle of 45 degree with sigma 2 and sigma 3. So, we can show now this plane number 4. So, if you consider your direction 1, sigma 1, sigma 2, sigma 3, then this making an angle of 45 degree with the direction 2 and 3. So, therefore, the plane is nothing but a typical plane of this type. This is the plane. And you can also have the plane which is making an angle with the minus sigma 3 and sigma 2 directions 45 degree. So, that is also the other plane you can consider. So, this is the other plane. So, these are the plane, 2 planes which are given by combination 4. Similarly, you can consider the planes given by 5 which is making an angle of 45 degree with direction 1 and 3. So, we can show this plane number 5, it is making an angle of 45 degree with direction 1 and 3. So, therefore, 2 and 3. So, it is making an angle of 45 degree. So, therefore, this should be the direction. So, a typical plane could be this one, and it can also considered to be another plane which is like this. So, these are the 2 planes which is nothing but plane 5. You can now do it yourself. The plane number 6 is going to make an angle of 45 degree with direction 1 and 2. So, therefore, it will be making an angle of 45 degree like this, 45 degree, and it will be in this quadrant. So, also you can take the other plane. So, I leave it to you to draw it yourself. Now, let us try to see what is the value of the maximum shear stress that we get on these planes. So, we had the expression for the maximum shear stress given here. So, maximum shear stress is given here. So, this tau square is equal to, if we consider the plane number 4, wherein we have m and n equal to plus minus half. So, let us consider the case m n plus minus 1 by root 2 and L equal to 0. Now, from this expression you find that tau square is nothing but 1 by 2 sigma 2 square, and here when you substitute this, this comes out to be this is going to be plus half sigma 3 square minus, here it is half sigma 2 square minus no, this will be simply half sigma 2, and this is going to be plus half sigma 3 square. So, once you simplify this, this is going to be equal to half, we can take common half and it will be like this, it will be sigma 2 square plus sigma 3 square minus, it will be half sigma 2 square plus sigma 3 square. So, this gives us 1 by 4 sigma 2 square plus sigma 3 square minus, this is again wrong. So, this is sigma 2 sigma 3. So, tau maximum is nothing but equal to half sigma 2 minus sigma 3. So, the maximum shear stress is going to be plus minus half sigma 2 minus sigma 3. So, the directions are 2 and 3 involved, and the principal stresses involved are sigma 2 and sigma 3, and the maximum shear stress is going to be like this. So, we can write now for the other two planes the shear stresses to be given by. So, you have the other, if you call it 1, then or it is plane number, let us say this is plane number 4, then we have tau max, plane number 5 is going to be given by plus minus half, this will be involved with sigma 1 and sigma 3. So, sigma 1 minus sigma 3, and the plane number 6 will be involved with plus minus half into, in this case directions 1 and 2 are involved, and then the stresses are sigma 1 minus sigma 2. So, these are the principal stresses, and it is nothing but the difference between the two principal stresses divided by 2, and they act at an angle or on a plane at an angle of 45 degree with these two directions. So, same is the case for plane number 5, which is at an angle of 45 degree with the directions 1 and 3, plane 6 it is at an angle of 45 degree with the direction 1 and 2. We will now consider determination of octahedral shear stress and octahedral planes. Rather, we will try to define octahedral planes, and we would like to calculate the shear stress on such octahedral planes. Again at a point we will have the three principal directions. So, with those as the reference directions, if we consider a plane which is equally inclined with the three principal directions, so we consider a plane which is equally inclined to all the three principal directions. Such a plane, let us say plane 1, it is known as an octahedral plane. Obviously, you can understand that the direction cosine of this plane would be L equal to M equal to N, and it is going to be equal to 1 by root 3. How many such planes will be there? In fact, in the positive quadrant we have such a plane. We can consider the quadrant formed by the direction sigma 2, sigma 1, sigma 2 and minus sigma 3. We will have another octahedral plane. So, therefore, in the upper half we will have 4 such octahedral planes. Similarly, in the bottom half we are also going to have 4 octahedral planes. So, there are 8 octahedral planes and they will form a geometry like this. So, you are going to have such 8 planes arising out of the 8 quadrants. The normal stress on such a plane sigma is going to be given by, just we have derived in the last lecture that sigma on this plane can be written in terms of L square sigma 1 plus m square sigma 2 plus n square sigma 3. So, this is the normal stress, and therefore, if you substitute the value, it will be sigma 1 plus sigma 2 plus sigma 3 by 3. So, it is the average of the 3 principal stresses and it is known as mean stress, and it is indicated as sigma n. So, this is the mean stress at the point P, if you would like to consider. So, if you consider that your typical point is P, so this is the mean stress at the point P. Since the sum of the 3 principal stresses are also equal to the sum of the 3 normal stresses in Cartesian coordinates, one can immediately write that this is nothing but sigma xx plus sigma yy plus sigma zz by 3 or sigma x plus sigma y plus sigma z by 3. So, these are the various forms of this mean stress. If we consider the resultant, if we consider the tractions on this plane 1. So, this plane 1 would have tractions S1, S2, S3. We can write S1 to be equal to L sigma 1, S2 to be M sigma 2 and S3 equal to N sigma 3. The resultant traction S is equal to S1 square plus S2 square plus S3 square, and this is equal to nothing but L square sigma 1 square M square sigma 2 square plus N square sigma 3 square. Now, once we substitute the value of the direction cosines 1 by root 3, 1 by root 3, we get the following. This will be 1 by 3 into sigma 1 square plus sigma 2 square plus sigma 3 square. We can also find out, if you consider that the shear stress on this plane is given by tau, then the resultant tractions can also be obtained by considering the fact that resultant tractions is nothing but sigma square plus tau square, and sigma is nothing but sigma m on this plane plus tau square. So, we can now get tau square is equal to sigma m square minus s square, and if we substitute the value we have gotten earlier, it is nothing but sigma 1 plus sigma 2 plus sigma 3 by 3 whole square minus 1/3 sigma 1 square plus sigma 2 square plus sigma 3 square. So, this is the expression of the shear stress, and if you now simplify this expression, tau square is equal to 1 by 3 I am sorry, it should be just opposite, this should be this way, and therefore, we will have the expression slightly different. So, this is it, and therefore, we will have it like this: sigma 1 square plus sigma 2 square plus sigma 3 square minus 1 by 9 sigma 1 plus sigma 2 plus sigma 3 whole square, and this can be simplified to the form, it is nothing but 1 by 3 sigma 1 minus sigma m square plus sigma 2 minus sigma m square plus sigma 3 minus sigma m square. Therefore, this stress, which is considered to be octahedral shear stress, it is indicated as tau with subscript OCT for octahedral is nothing but plus minus 1 by root 3 into sigma 1 minus sigma m square plus sigma 2 minus sigma m square plus sigma 3 minus sigma m square, exponent with exponent 1 by 2. The alternate forms, you can have alternate forms of toy octahedral. So, we can write now tau octahedral to be given in this form 1/3 sigma 1 minus sigma 2 whole square sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square raised to the power half, and it can be also written in terms of the Cartesian components, which is nothing but 1/3 sigma x square plus, I am sorry, this is sigma x minus sigma y whole square sigma y minus sigma z whole square plus sigma z minus sigma x whole square plus 6 times tau xy square tau yz square tau zx square raised to the power half. It can be also written in terms of the stress invariance. This is also given in this form root 2 by 3 I1 square plus 3 I2 raised to the power half. So, the octahedral shear stress is something, has some significance attached. We know that this I1, I2 are stress invariants, they are not dependent on the selection of coordinates, and this relation between the two stress invariants and the octahedral shear stress is indicative of the fact that the toy octahedral shear stress is also an invariant. So, it is an invariant quantity. We look into the breaking up of total stress tensor into components like deviatoric and hydrostatic stress tensors. If you consider the stress tensor at a point sigma ij, which is given by this matrix, Now, the mean stress at the point is given by sigma x plus sigma y plus sigma z by 3, which can be also written by this tensor notation sigma I by 3. Since these indices I are repeated, it implies a summation. This means that this is equal to sigma xx plus sigma yy plus sigma zz by 3. Now, if we try to break up this stress tensor into two parts like this, we have here sigma x minus sigma m, this remains as it is, this also remains as it is. Then in the second row, we are simply amending this stress in the y direction, and in the z direction we are amending the stress in the z direction. Plus we have this sigma m, sigma m, sigma m in the three directions. This can be written in tensor notation like this. This first part is sigma I minus delta I j into sigma m plus delta I j into sigma m. Delta I j is nothing but the Kronecker delta. This first part is known as the Deviatoric stress tensor. It is also known as distortion part of the stress tensor, and the second part is the hydrostatic stress tensor. It is also called spherical stress tensor or volumetric part of the stress tensor. These two parts have distinct roles. The deviatoric part is responsible for the deformation of the element, and hydrostatic part is responsible for the change of volume of the element. This hydrostatic part does not give rise to any distortion of the element. Similarly, this deviatoric part is responsible only for the deformation, but it does not give rise to any change in volume. And you will find that under the action of this deviatoric part, any two orthogonal directions will change orientation. That means, if you think of the angle between the x and y direction before deformation, after deformation they will undergo change. So, there will be shear deformation. So, this is the effect of part 1. On the other hand, if we consider the hydrostatic part or hydrostatic stress tensor, this is going to give rise to change in volume of the element, which can be represented in two dimension like this. It is possible to find out the direction of the principal stress just considering this deviatoric part of the stress tensor, and the total principal stress can be again obtained from the principal stresses arising out of the hydrostatic part, and after adding the mean stress. I would like to explain this point. So, if we consider the hydrostatic part to be delta Ij sigma m and the deviatoric part sigma Ij minus delta Ij sigma m. So, let us represent this thing by sigma ij dash. So, this is really the, in our earlier notation, this is part 2 and this is nothing but part 1. Now, we can go for considering only this part 1. So, this is sigma ij dash. If we write the equations involving the principal directions, then it will be in short form like this: Lj sigma ij dash minus delta ij sigma dash following the steps as we have done in the case of the total stress. We will get the equations involving the direction cosines of the principal directions given by this equation. So, this is, let us say, equation number 1. To expand this, it will look, if I consider that Lj has components like L, M and N, then we will get the equations like this: sigma x dash minus sigma dash plus m into tau xy plus n into tau xz equal to 0. Similarly, we will have L into tau yx plus m into sigma y dash minus sigma dash plus n into tau yz equal to 0, and the third equation is tau zx plus m into tau zy plus n into sigma z dash minus sigma dash equal to 0. So, this set of equations will have solutions for the direction cosines L, M and N, provided we have the determinant, of the coefficient matrix, that is sigma ij dash minus delta ij sigma dash equal to 0. So, this is the characteristic equation giving an equation involving this sigma.